So in this problem, we're going to use the Arrhenius equation to calculate K at one temperature from K at another. So what you really want to be doing here is using the 2-point form of the Arrhenius equation. Now, once you've got that 2-point form and you've got all your numbers kind of straight, you can either use the solver to solve for the unknown K, or you can do algebra and solve for it. The important thing to recognize is that make sure that your answers are consistent with the concept that as the temperature increases, the K should become a bigger number. So you always want to double check that at the end. So the rate constant of a certain reaction is known to obey the Arrhenius equation and to have an activation energy of 28 kilojoules per mole. It's important to remember that you want to turn your activation energy into joules. So that's going to be 28.0 by 10 to the 3 joules. And that doesn't change with the temperature. And then it says that the rate constant, let's just call it K1, is 8.4 by 10 to the 6. And it looks like this is a second order reaction at 202 degrees Celsius. So that's going to be our T1, but we've got to turn that into Kelvin by adding 273 to it. So that's going to end up being 475.15 Kelvin. Okay, there we go. All right, so we've got that. So then, and then it says, what will the rate constant be at 268 degrees Celsius? Well, what I can tell you is it's going to be bigger than what it is at 202 degrees Celsius. So K2 is what we're trying to find. And then we want for our T2 is going to be 268. So I'm going to use the calculator for that. 268 plus 273.15 gives me 541.15 Kelvin. Okay, so now I'm ready to roll with my 2-point form of the Arrhenius equation, which goes like this. Log K1 on K2 equals minus EA on R 1 on T1 minus T2. And we want to solve for K2, right? So what I'm thinking is the easiest thing to do here is to use the solver. Now, you can do this in a couple of different ways. You could use one on, say, a website like Wolfram Alpha. I'll show you that in a moment, or you can use it in your calculator. So for me, my solver in my calculator requires that my equation equals 0. So I'm going to just reorganize this guy so that it equals 0. And to do that, I'm going to add the EAR 1 on T1 minus 1 on T2 terms to both sides. So now I can put that into my calculator, and what I'm going to do is I'm just going to solve. I'm just going to let that equal x. So I'll bring up my calculator and show you how I'm going to go about doing that. So I'm just going to roll out a little bit so I can see everything. There we go. Okay, so let's put my calculator up and you'll see how I do this. So for me, I'm going to turn the calculator on. So to get to my numerical solver, I go math, I go up 1, and it says solver, and then I'm in. First thing I'm going to need to do is enter my formula, and you can see here how it always sets it so it equals 0. So it's going to be log of K1, which was 8.4 by 10 to the minus 6, divided by K2, and now K2 is my X, so I'm just going to hit the X button there, there it is, plus my EA, which was 28 kilojoules, right, so I have to do that by 10 to the 3, divided by R, and I need to use the 8.314 joules per mole for my R, and then multiplied by 1 on my T1, and my T1 was 475.15, minus 1 on my T2, which was 541.15, and there we go. Okay, and so now what I need to do is I need to put in when I press enter, it's going to ask me to put a guess in for my X. And all I know is that it's going to be bigger than 8.4 by 10 to the 6. So why don't I put it in as 9 by 10 to the 6, okay? Now, if I want to, I could change the bounds, but I'm not going to bother. So I'm just going to solve from here. So I'm just going to go alpha, solve. And it didn't work. So let's see if we can problem shoot what we've got wrong here. And it's pretty easy. I put a -6 there instead of the actual 6. So everything else is good. So alpha, solve, and boom, it did it. So now when I quit, I want to get my x. I just go x and press enter, and I'm told what my x is. Now, I'm asked to give my answer to 2 significant figures. So that would be easier if this was in scientific notation. So I'm just going to go mode, over to scientific notation, enter, then quit out of here, and then I'm going to get the calculator to tell me what x is again. And it was 1.9 by 10 to the 7. So it's about double what it was before, which is brilliant. So 1.99 by 10 to the 7 to 2 sig figs, that's got to be 2.0 by 10 to the 7. So my K2 equals 2.0 by 10 to the 7. My units don't change. So to be molarity to the -1, seconds to the -1. Now, I'll quickly show you how to do this in Wolfram Alpha as well. And this is kind of even easier still. So what we'll do here is we'll go over to wolframalpha.com, right? And so we'll just put our formula in, log of K1, and we'll just look at that. It was 8.4 by 10 to the 6, 8.4 e to the 6 on x, right, equals minus EA, which was 28 kilojoules? Let's have a look at that. 28 kilojoules, yeah, on R, 8.314, multiplied by 1 on our T1, and our T1 was 475.15, minus 1 on T2, which was 541.15. Then close parentheses, and then in this case all you have to do is just hit the little equal sign at the end, and it'll, most of the time it'll solve for x for you. Here it goes. And same answer, right? Okay, so 1.99 by 10 to the 7. So 2 ways of solving these problems. I really like Wolfram Alpha. It's arguably a little easier than the calculator. We got the same answer both times. Okay, so 2.0 by 10 to the -7 per mole per liter per second.